is working the Chapter 5.8 review problem. It's a comprehensive graphing polynomials problem. So there's several steps to this problem, and I broke them down into pieces, just like the steps that I gave you as to how to graph a polynomial. So let's get ourselves a graph going here. Okay. Put that over here in the corner so we can kind of graph as we go along. And I'm going to look at part A. So part A says, the first question is, what is the degree of f of x? Well, it'll take a little bit of time to kind of get comfortable with this, but basically what I do to determine the degree, means the highest power of x in this polynomial, is I could FOIL this whole thing out and put it in standard form. That would take a long time and be very painful. Instead, what I'm going to do is I'm going to see, well, this piece right here, clearly the highest power of x, if I wrote this out as x minus 3 times x minus 3 times x minus 3, the highest power of x, if I FOILed all that out, is going to be cubed. So, well, let's write that again. X minus 3 times x minus 3 times x minus 3. The highest power is when we always do our first, so it's going to be x times x, which is going to give me an x squared, and then later it's going to be x squared times x, which is going to give me an x cubed. So the highest power of x right there is going to be x to the third. Get it out of the way. There we go. Okay. This is going to be the highest power is going to be 3. And in this one here, similar process, the highest power is going to be 2. And in this one here, the highest power is going to be 1. And for this little x standing all alone by itself, the highest power is going to be 1. So the degree of this polynomial is going to be 3 plus 2 is 5, plus 1 is 6, plus 1 is 7. So the degree is going to be x to the 7th. Now, just to take a little detour here, I don't have this, so I'll write it in a separate color. But if I had x times x squared plus 1 times x minus 1 squared times x minus 3 cubed, I would have a degree of 3 plus 2 is 5 plus 2 is 7 plus 1 is 8. So that would be a degree 8. Or if I had, if I had x times x squared plus 1 to the third times x minus 1 squared times x minus 3 cubed, the degree of this little segment right here is 3. The degree of this one is 2. The degree of this one is 6. And the degree of this one is 1. So this would be of degree 7, 8, 9, and 11. So that would be x to the 12th. But we're not doing that. We're just doing what we had. So our highest degree is x to the 7th. What is the sign of its leading coefficient? Well, I don't see any negative signs in front of any of the x's that I have here. That's telling me that my coefficient is going to be positive. Now, if I had had a, let's say, a negative right in there, so it's negative x minus 1 squared, that negative would kind of translate it over here to the front, and then I'd have a negative leading coefficient. But I don't have a negative leading coefficient. I don't have any signs, I don't have any positive signs in front of it or negative signs in front of my coefficient. So it is a positive leading coefficient, and that tells me what is the end behavior. I have an odd highest power, a positive leading coefficient. It's going to follow the same format as x cubed. So my end behavior is going to be down, up. And what I like to do on a graph, just so I kind of, when I'm beginning to graph this out, is I'll just put some arrows here that show me it's going to be a down, up graph eventually. So that answers part A. Part B says, what is the y-intercept? Well, remember, any place that I have a y-intercept, you can see all of them. value of x is going to be 0. So the value of x is going to be 0 where I have a y-intercept. All I need to do is substitute 0 in for x in every part of this polynomial. Well, actually, in this particular polynomial, it's pretty easy because I have 0 times 0 plus 1 times 0 minus 1 squared times 0 minus 3 cubed. And since I'm starting off with a 0 times everything, I know that my y-intercept is going to be at 0. So that right there, 0, 0, is going to be my y-intercept. Now again, not this problem here. But let's just say that I didn't have that first x as part of my polynomial. I do, but let's say that I didn't. Then my y-intercept would be, well, 1 times negative 1 squared times negative 3 cubed. And that would be 1 times negative 27. My y-intercept would be negative 27. I don't have that. I just wanted to show you an example here of how do you find your y-intercept. Y-intercept is really easy to find. You just set every x equal to 0. I know you're comfortable doing that when it's in standard form, but you can do it also when it's in factored form like this one is here. Okay, so we found my y-intercept and I plotted it. What are the x-intercepts? Well, x-intercept means y is going to be equal to 0. Well, fortunately, I have this in factored form right up here. So I can figure out pretty easily what my zeros are going to be. What values of x are going to give me a 0 for y? Well, this one right there will be 0. Because if I get 0 for x, I'm going to have 0 for y, and I've actually already plotted that point. Here, it's going to be negative 1. Here, it's going to be positive 1. And here, it's going to be positive 3. So all of those are going to be x-intercepts. So I plotted the 1. There is 0, 0. I'm going to plot 1 at negative 1. I'm going to plot 1 at 1. And I'm going to plot 1 at 3. So I can see that I have 4 x-intercepts. And I'll just write them down here again. Negative 1, I'll put a little set symbol, 0, comma, positive 1, positive 3. Now, I made you a little graph to be able to chart this out and help you make this make our graph. I made a little chart here. So I have 4 zeros. I have the one at negative 1, the one at 0, the one at 1, and the one at 3. And I need to determine what is its multiplicity and whether it is a touch or a cross. So I'm going to go back up here to my factors here. And when I'm talking about multiplicity, what I'm asking is kind of how many times does that 0 occur? So, for example, if I looked at this factor right here, well, that's x minus 1 squared, which is the same thing as if I said x minus 1 times x minus 1. It happens a multiple of 2 times. So the multiplicity is 2. Now, that's not saying it's like literally touching that point twice. It's just saying it's a multiplicity. It would happen 2 times. So let's get rid of that. So the multiplicity is the same as the power of the factor. So I have at x, at negative 1, I have a multiplicity of 1. At x equals 0, that's x equals 0. Whoops, wait. X equals negative 1. Negative 1, that's this one here. I have a multiplicity of 1. It's the power of 1 right there. Where x equals 0, I also have a multiplicity of 1. Where x equals 1, well, that's squared where x equals 1. So I have a multiplicity of 2 right there. And where x equals 3, I recall from looking back at it, it is cubed. So I have a multiplicity of 3. And the key thing about multiplicity is it's telling me whether the graph either touches or crosses the x-axis. If it is an even multiplicity, it is a touch. If it is an odd multiplicity, it is a cross. And just to kind of, again, show you how I remember that, I'm going to go back to my old standbys of x squared and x cubed. So this is the same thing as x minus 0 squared. This is the same thing as a factor of x minus 0 cubed. The graph of x squared comes down here, and it just touches right there at the 0, and it goes back up. It's an even multiplicity. It touches. The graph of x cubed looks like this. Comes up, and at 0, it crosses. Okay? It's an odd multiplicity. It's a cross. So that should make it easy to remember that. So when I have my, let's go back to my chart here. At -1, it's going to be a cross. At 0, it's going to be a cross. At -1, it's 2, it's even. It's going to be a touch. And at 3, it's odd, it's going to be a cross. So frequently I'll come up to my graph, and I'll go, okay, well, this is going to be a cross, that is going to be a cross, this is going to be a touch, and that is going to be a cross. So I filled in through part D there, and now I'm on part E. And it says, based on your answers from A through D, sketch what you think this graph might look like. You are not expected to identify the y value of any turning points. I don't know how high or low the turning points are going to be. I can't find that out unless I use my calculator or unless I know a little bit of calculus. But I can kind of sketch out what I think this graph is going to look like. Because I know my end behavior is going to start from down here, and it's going to come up to this point right here, and it's going to cross it. Because it says so. And if it's going to cross at the next 0, that means somewhere around here it's got to turn around, and it's going to cross. And then if it's going to touch at the next 0, it's got to come up, and it's got to touch it, and then go back down. It's just touching. And now it's got to turn around again, and it's got to be a cross. That's the last 0 that I have. This seems to match up with my end behavior that I had penciled out. So I think my graph is going to look something like that. Well, let's graph it and see. You can see I entered it in here into my calculator, which just popped up magically on your screen. And I'm going to go zoom 6. There's my graph. Well, it looks kind of like that. I think it might look like that a lot. But I'm going to kind of widen it out a little bit. So I can see most of the activity is happening between like here and here. So I don't need really to see all these x points over there. If I don't need to see all those x points over there, I won't. What I'm going to do then is I'm going to go to my window, and I'm going to, instead of going all the way to -10 on the left, I'm just going to go to -4. And instead of going to 10 all the way on the right, I'm just going to go to +4. And I'll leave my scale at 1. Now I'll push graph and see what it looks like. Well, that's a little bit better. And again, it's starting to look like what my graph looks like. I'd like to see the whole thing, though. And I can see that I'm going kind of way up here. I can see my bottom points, but I can't see my top point. I don't know exactly what it is, but I'm going to make an estimate. So I'm going to change my window again. And I'll change my window. I'm going to change my y values. I can leave my minimum at -10 because I know that that lets me see all my minimums. And my maximum here, I don't know, let's change it to 25. And I'll change my scale to go in 5s. So I'll push graph. Did that help me? Not quite. Let's take it up to 35. Window. I'll take my y max up to 35. And I'll push graph. That's better. So I kind of see now, and yes, indeed it does look like what my graph looks like over here. Now, yes, I didn't make this turning point right there as high as it might be. But it doesn't matter. That wasn't what I was getting at. I still have the situation where I'm crossing here at -1. I'm crossing again at 0. I'm coming back around, I'm touching right there at 1, and I come back down, and I'm crossing at 3. So the shape of my graph, as I had predicted it would look, does look similar to what I have on the actual calculator. So this was part D, and part E was the graph. So let's go to part F. Part F says, how many turning points are there? Does that make sense? Explain why. So I'll go to my graph since it's a little bit bigger and easier to look at. How many turning points are there? Well, turning point is where it changes from either going up to down or down to up. So I'm going up, 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 and I have a turning point right there. And then it's going down, it crosses through the thing, it's still going down, and I have a turning point there. Then it turns around, I have another turning point there, and I have a final turning point there. So I have 4 turning points. I have 4 turning points. Is that reasonable? Yes, I think that's reasonable. My function is of degree 7, and the most number of turning points I could have is 6. Well, but I can have less than 6. So 4 is certainly less than 6. So yes, that makes sense. So I would say max turning points is 6, comma, or semicolon, 4 is less than 6. It makes some sense. That's a reasonable explanation. Now I have to list the y value of all of my turning points. And I cannot do that without calculus or without a calculator. So right now we're going to do it as a calculator. And what I need to do with a turning point is a maximum or a minimum is a turning point. You can kind of see that where I have a, let's make this go away here, on my graph here, where I have a turning point, I have a maximum spot in a particular neighborhood. And that's the way I like to look at it. I like to look at it as if it's a particular neighborhood. So let's kind of make ourselves a graph and make sure I can explain what I'm talking about. There's my x and y axis. Here are some minimums and maximums. Okay? So I have turning points. I have 1, 2, 3, 4, 5, 6. I have 7 turning points on this graph. That means this graph has to be at least of degree 8. And I will also tell you that this graph is also going to have a negative leading coefficient because my end behavior is down, down. So I have even end number of even power and a negative leading coefficient down, down, 8 turning points. Each of these turning points is a local minimum or a local maximum. And by local, it means I'm describing a neighborhood. So this is a neighborhood right there. The neighborhood encompasses either one minimum or one maximum. That's a neighborhood. So I'm going to call it neighborhood, N-E-I-G-H-B-O-R, hood. And the technical word for that is an interval. So in this interval right here, I have one local maximum, which is a turning point on the graph. How do I find out what that value is? Well, I'm going back to my graph here. And first I need to define my neighborhood. So I want to do my first maximum over here. So I'm going to go, I'm looking at the graph, I'm going to go second, calc. And I want to find a maximum, number 4. So it's asking me, what is the neighborhood you want? I have to give boundaries for my neighborhood. I have to give the left boundary and the right boundary. Well, I can see that a left boundary for that top maximum right here, that's the maximum I'm looking for. If I go to -2, that'll certainly be far enough to the left. And now it's asking me for my right boundary. Well, I can see that 0 would be a good right boundary. I could use that. I could use a little bit less than 0. So I'm going to use -0.25 as my right boundary. And you'll notice let me erase my red dot there and put another couple red dots. You'll notice these two arrow thingies right there. They are pointing, they are defining the interval. They are defining the neighborhood. So my maximum is certainly within that neighborhood. The computer, the thing has asked me, do I want to make a guess? No, I don't want to make a guess. That's why I bought the calculator. That joke never gets old to me. So I press no, I don't want to make a guess. And you'll see the cursor then goes right to the maximum. And the maximum says my x value is negative 0.7. I'm rounding off to one decimal here. And my y value is 30.7. So the way I need to write this, there's a clear, specific way it needs to be written. You would say that f of x has a maximum of 30.7. 30.7. That's the y value at x equals negative 0.7. It's important to know that way to write that terminology. And you would do that similarly for minimum. So if I'm going to do a minimum, let's get on the page here. I want to find my minimum. Let's find my first minimum, which looks to be this spot right there is minimum. So let's find it. I'm going to go second calc, and I'm going to go minimum, that's 3, and it wants to know my neighborhood. Well, I could start up there. I don't like to start at maximum or minimums, just in case I'm a little bit to the left, a little bit to the right. So I know that that one is to the right of 0, so I can make my left bound. I'm going to make my left bound 0. That's okay. And I can see that my right bound, I'm going to hit another maximum over there. I'm going to be in a different neighborhood at x equals 1. So I'll make my maximum a little bit less than x equals 1. I'll make my maximum at or my right bound at 0.9. So I go enter, and it looks to me like I'm in a pretty safe interval there. Looking at my little arrows here, they look like they are going to cover the neighborhood where I have my minimum that I'm looking for. So I don't want to make a guess. And it tells me I have a minimum. So my x value is equal to 0.3. My y value is equal to negative 3.8. So I have a minimum of negative 3.8 at x equals 0.3. That's the format. The minimum is the y, or the maximum is the y value. So I'm not going to go through all four. I'm not going to go through all four of the turning points. Although there is one of these turning points that you don't even need your calculator for, and that is the one. In fact, any turning point that has a multiplicity, an even multiplicity, even multiplicity is a touch. Well, by definition, if it's a touch, if here's your x-axis, it's either going to touch like that, or it's going to touch like that. That spot right there, the x-intercept, is also either the minimum or the maximum. So I know on my graph that this point right there is a local maximum. So I have a local, I can write the word local. I have a local maximum of 0, that's the y value, at x equals 1. That one I don't even need the calculator to do. Just to show you though, let's make sure. I'm going to go second calc. I want to find a maximum number 4. I can see that it's between 1/2 and 3/2, so I'll put my left bound at 0.5, and I'll put my right bound at 1.5. Yes, my interval looks like it's in the right neighborhood. I'll press enter. Notice, because it is a calculator, it works on pixels. It's telling me my maximum is my x value is 1.000011, and you have to assume that this really means 1. So x is equal to 1, and y, it says negative 2.07 e to the negative 11. So what would that be? That would be negative 2.07 e to the negative 11. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to run out of room. All these zeros are going to be here in front of that negative 2. That is essentially equal to 0. So you have to kind of trust your intuition here a little bit, and you would say that I have a maximum of 0 at x equals 1. And if you wanted to test it, you could go to your calculator, and since you've entered that function in, you could go to your main screen, and you could go alpha F4, choose your y1 function, that's where you put that function. Let's evaluate that function for x equals 0. No, I'm sorry, for x equals 1. That's the x value. X equals 1. And it tells me it's 0. If it wasn't really 0, it would give me a bunch of decimal points, but it is. So that's how I can kind of list all my turning points. Finally, let's go back to the graph. It's asking me for the domain of the function, and it's asking me for the range of the function. It's a polynomial. Polynomials, the domain of a polynomial is all real numbers, negative infinity to positive infinity. That is the domain of a polynomial. In this particular polynomial, the range is the y values. This has down, up behavior. It's going to go down forever. It's going to go up forever. The range is going to be negative infinity to positive infinity. The only time with a polynomial, the domain is always going to be all real numbers, but sometimes the range might not be all real numbers. And where the range won't be all real numbers is if I have a highest power with an even exponent, whether it's positive or negative. Because if I have a highest power with an even exponent, if it's positive, it's going to have up behavior. And if it has up behavior, it means at some point in time, it has to turn around for the last time. And that point there will be the lowest part of my range. So let's just say that number right there is y equals -1. My range would be -1 to infinity, because it goes up to infinity. If it was a negative leading coefficient, my polynomial would have down behavior, down, down. Whatever the highest point where it finally turns around at the highest point for the last time, not necessarily for the last time, it turns around there too, but this is the highest point where it turns around, that then would be my maximum. So let's call that y equals 3. My range would be negative infinity, because it does go down forever, to 3. Actually, this should have been a bracket, because I should have included one right there. So that would be my domain and range of the function. So that's a lot of stuff on graphing a polynomial, but I know it's really kind of fun. It's a cool little puzzle.